Okay, so this is the multiple choice. Represents an atom that's in an excited state. In a positive, it's lost one electron. It's not in its normal ground state. Number 2, atom that's a noble gas. So our only noble gas here is Xe. Remember, the noble gases are located over here. Number 3 represents an atom that's a transition metal. The only one here that's in the middle section of the periodic tables is Ni. And then number 4 represents an alkali earth metal, Ca. Ca, these are the alkali earth metals right here. And so number 4 is Ca. Skipping down here, going to questions 9 through 12. A reaction that's both a weak acid and a strong acid. So acids, as far as we know right now, all start with H. And so you can find an acid right here, H2SeO4, which obviously is not hyperhickyl high, honohickyl low, H2SO4. Those are the only strong acids that we know. And then it also has HCl in it, which is written dissociated, which it should be because strong acids completely dissociate in solution. And so think of this as being an ionic equation. And so letter A right here would show a weak acid plus a strong acid. This is not an acid, this is not an acid, these are not acids, these are not acids either. And so letter A is the only one that has a weak and a strong acid in it. Number 10, precipitation reaction in which Sr could be a spectator ion. So a precipitation reaction, remember, is one that's going to form a solid. And so we have to look through these to find one that forms a solid, and it turns out there's 2 that do right here, both D and E. And so we're kind of narrowed down to those 2 possible ones. And then it tells us Sr plus 2 could be a spectator ion. So a spectator ion means one that's not going to react or form a solid with something else. And so in letter D, if we put strontium plus 2 in there, the positive would react with the negative right here, and we would form some strontium sulfate. Now, that would be okay if strontium sulfate were soluble, and it would form Sr plus 2 and SO4 2 minus over here, because then those strontiums would cancel out with one another. But if you look on your periodic table, it says all sulfates are soluble except for, and then it has strontium sulfate right here at the end. And so strontium could not be a spectator ion in this reaction where there's a bunch of sulfate ion around, because it would have to be in the net ionic equation right here, showing that it would form strontium sulfate solid. How about down here in letter E? Could I put strontium ion in there? Strontium ion would, being positive, would react with the negative ion chlorine right here, and it would form SrCl2. Now, is that one soluble? Well, all chlorides are soluble except for silver, mercury, and lead. Oh, strontium's not included in that. So strontium would end up being Sr plus 2 and Cl minuses, and the strontiums would cancel out. And so in letter E right here, strontium could be a spectator ion and do nothing in their reaction. It could not be in letter D, though. Number 11, in a reaction in which the same reactant undergoes both oxidation and reduction. So remember, redox reactions are one where something goes up in charge is oxidized, and down in charge, remember, is reduced. And so let's go through and let's zoom in on letter C right here, and let's take a look at what I2's oxidation number is. It's 0 because it's alone by itself. And then oxygen, of course, is -2, and hydrogen is +1 in OH minus. And then over here on the right-hand side, we have 5I minus, which means that iodine is -1. So we already see iodine went from 0 to -1, so it went down in charge, so I do have something that's being reduced. And in the next species, I have IO3 -1. Oxygen, of course, is -2 because it's always -2, except for in peroxide or when oxygen is alone by itself, which means that oxygen here has to be +5 because this has got to add up to equal -1. So in this case, iodine went from 0 to +5. It went up in charge, and therefore it's oxidized. So here's my species, and it was both oxidized and it was reduced. And so letter C is my answer for number 11. Number 12, a combustion reaction is where we're going to form carbon dioxide and water when there's a hydrocarbon reacting with oxygen and giving off heat and flame. And we can see that in letter B right here, we have a hydrocarbon reacting with oxygen, and it produces carbon dioxide and water right here. So 12 is letter B. Next page. We have an aqueous solution of potassium phosphate. It's a better conductor of electricity than an aqueous solution of potassium bromide. Which of the following best explains this observation? So first of all, take and write down your two equations, K3PO4 and the other one is KBr. And when these dissolve, these are going to give you aqueous solutions of ions. This one is going to form 3 K pluses and a PO4 3 minus. This one is going to form a K plus and a PO4 3 minus. So now take a look at the number of total ions this will form. This one's going to form 3 potassiums and 1 phosphate for each formula unit of K3PO4. So you're going to get 4 particles, or 4 plus and minus things. Here you're going to get 1 K plus and 1 PO4 3 minus. And so you're going to get 2 plus or minus things. And so which one is going to give you more pluses and minuses? That's the one that's going to give you more electrical conductivity. And so letter D says right here, more moles of ions are present in a given volume of 0.1 molar K3PO4 than in the same volume of 0.1 molar. Because you're giving 4 for every 1 formula unit here, here you're only getting 2 for each formula unit. All right, moving on, number 14. This one gives us the element rubidium, contains 2 isotopes. So we have rubidium with atomic mass of 85.47, and it has 2 isotopes, rubidium 85 and rubidium 87, right here. Which of the following statements about the isotopes of rubidium is correct? So we can see that the average atomic mass right here is a little bit smaller than if we had 50% and 50%. Because if I had 50% rubidium 85, 50%, and 50% of 87, now I would have an average of 86 for my molar or atomic mass. I don't have that. I have a little bit less, which means there's going to be more of this rubidium 85 in there to determine it. Now you could do a mathematical operation to figure this out because it's a weighted average, and so you could say that there would be a percentage, an amount, in this case I said 50% or 0.5 of 85 plus an amount of 87. Now they have to total up to equal 1 because that's the total of both percentages. Now I could say 100% if this were 50% and 50%, but I use decimals. And so my 100% minus whatever 85 is going to be my amount that is 87. And this is going to have to end up equaling 85.47. Now if I figure out x, or solve for x in this equation, I will know the percentage that is going to be 85. And then I can decide whether that means the 85 is going to be twice as abundant as 87, 3 times abundant as 87, or 87 is going to be twice as abundant as 85, or 87 is 3 times abundant. And so I'll leave the algebra to you to solve for x right here, but the answer ends up being letter B right here, that 85 is approximately 3 times as abundant as 87. So you should end up with something that's about 3 times as abundant as this when you do the math to solve for x here in number 14. Number 15, how many protons, neutrons, and electrons are in 39K19 with a little plus sign right here? So this, remember, is my atomic number. That should match the atomic number on the periodic table for potassium, which it does, 19. This is my mass number, and my mass number tells me the number of protons plus neutrons in the nucleus of that substance. And then this, of course, tells me what charge it has, and that tells me how many electrons have either been gained or lost. Now, at start, the number, let's start right here with electrons. The number of electrons normally equal the number of protons in a neutral atom, and so I'd say there'd be 19 protons and 19 electrons to start with. but there's a plus sign right here, which means I have lost an electron. So now I don't have 19 electrons, I have 18 electrons. And then to determine my number of protons in here, my number of neutrons in here, I could do 39 is equal to my number of protons plus my number of neutrons. And of course, this would have to end up being 20. So there are, in order right here, protons 19, neutrons 20, and electrons 18, which is number C, or letter C. Number 16, which two species contain the same number of electrons? So they give you some tricky ones right here. They give you Na with a little plus sign, and then Ar in letter A. And let's just go through this one as an example, because it's not the right answer, but we'll just look at it. And so Na would normally have 11 protons and 11 electrons, because it's got the atomic number 11 right here. But it has a little plus sign right here. So it's going to have 11 protons and it's going to have 10 electrons. One less electron, that's what gives it the positive charge. Now, argon on the periodic table has 18 protons and 18 electrons. Those do not match. They do not have the same number of electrons. Why they put that in there as a distractor? Maybe to make you trick and think that you're supposed to, move way over here or something like that. I'm not sure. But let's look at the correct answer now, which is letter B. And this one is F minus and Na plus. So we already looked at Na plus, and we said that that has 11 protons and 10 electrons because we lost one electron to become positive. And now it has a configuration like neon, 10 electrons. Fluorine now has a minus sign, which means it gained one electron. So normally it has 9, but now that it gained one electron, it also has an electron configuration, or electrons, like neon would. And so both of these have 10 electrons. These are called isoelectronic species. You can go through and look at the other ones too, and those don't end up having the same number of electrons either. Okay, we're on to number 21. And this says, an unknown metal melts at high temperature, is insoluble in water, and does not conduct electricity in the solid or liquid states. This substance is most likely to be. So first of all, it's an unknown solid, okay? All elements in the periodic table are solids except for mercury and bromine, who are liquids at room temperature. And then your gases, which are these guys over here, okay? So you know it's going to have to be one of these solid things over here, not one of these gases, and not mercury or bromine. Then it says it melts at a high temperature. Okay, it's insoluble in water, so it's not going to dissolve in water. And it does not conduct electricity in the solid or liquid states. So good conductors of electricity are metals, and metals are these guys over here. So that means it's going to have to be something from over on this side of the periodic table, because those are non-conductors. Those are the non-metals. So let's look through our possibilities. Aluminum right here, well, this is a solid, yes, but it would be a good conductor of electricity because aluminum is a metal, okay? Iodine, okay, this melts at a high temperature. It does not conduct electricity. This one would not conduct electricity. It would be a non-metal, insoluble in water. That is true. But one of the tricky things with iodine is that iodine does not go from a solid to a liquid at room temperature and pressure. It goes from a solid to a gas. Iodine undergoes what's called sublimation. So it cannot be iodine at room temperature. It would, or at a higher temperature, it would go directly to a gas, not to a liquid. So we can't choose B. CO2, well, CO2, a lot of people know, is both nonmetals, so that's good. It would not conduct electricity, but it's not a solid at room temperature. CO2 is a gas, so you can't choose that one. SiO2, so silicon dioxide, that's made of a nonmetal and a nonmetal. Okay. Maybe you learned this in earth science class, but SiO2 is a rock, or it's a solid, and some people call it sand. Okay, yeah, that's what SiO2. When it undergoes lots of heat and pressure, it forms super solid sandstone, and then even more eventually can go to glass. Okay, and this, it would not be a good conductor of electricity, so that'd be your best choice right there. And then letter E, of course, nickel, that's a solid, but it would conduct electricity because it is a metal. Okay, so maybe you learned something while we went through that one. Then number 23, which of the following solution contains the largest number of moles of solute? So now we're asking about the molarity triangle right here, and we're going to ask how many moles are dissolved in each one of these. And so let's look at each one, and we'll do a little bit of math to find the number of moles in each one. So there are 50 cubic centimeters right here, and remember, a cubic centimeter is the same as a milliliter, so we actually know the number of milliliters right here. And this is hydrochloric acid, HCl. And so 50 cubic centimeters would be 0.050 liters times 1 molar. And so my number of moles of solute would be 0.50 moles. Okay, now technically hydrochloric acid would break up into H plus and Cl minus, so I'd get a mole of this and a mole of this in there. But we'll come back to that in a second. Next is 0.025 liters of 5 molar sodium chloride. NaCl would also break up to give you some Na pluses and some Cl minuses, so 2 particles. And 0.025 times 5, 0.025 times 5 gives me 0.125 moles of this solute. Then in letter C, it's 100 cubic centimeters, so 0.1 liters times 0.5 molar, I think that says 0.5, nitric acid. So this would give me 0.05. And nitric acid, remember, again, is a strong acid, so that would also give you 2 particles per 1 particle that breaks up. But this is still way smaller than these guys right here, and because it wants to know which one's going to give you the most, or the largest number. And then the last one is sulfuric acid, spelled kind of funny. 5123, so 0.050 liters times my 2 molar, so 0.05 times 2, that's going to give me 0.1 moles of it. And H2SO4 is going to give me 2 particles as well, H plus because HSO4 minus right here, H2SO4. So every single one of them is going to give me 2 particles in solution, 2 particles. So all I have to do is take a look and see who's going to give me my most moles right here, and my most moles are going to be 0.125 right here in number 23. Letter B is your answer. Number 27, which of the following processes are exothermic? So this one probably would not show up on this particular exam, but exothermic means that energy is released, and so that's when something goes from a solid to a gaseous phase, you would have to put energy in to separate those particles because they're going from a condensed state, solid. Solid is the most condensed, liquid is kind of the middle, and gas is the farthest apart, so the particles are the farthest apart, and so you have to put energy in to separate those. And here the particles are the closest together. Here they're kind of in the middle. Here we have a gas going to a solid, so we're going from gas to a solid, so a bunch of energy would be released here in number 2. And then in number 3, we're going from liquid to a gas, so we're going from kind of middle together to quite far apart right here. So that's why 2 only would be your best choice. Number 29. In which of the following series are the elements arranged in the order of increasing electrical conductivity? So on the periodic table, remember, metals are the things that are the best conductors, and things that are the most metallic are over here on this side of the periodic table. things that are the least metallic would be over here on this side of the periodic table. So if you were looking at which one would be the best electrical conductors, you'd want to pick the ones that are over here first and these last. So if you look at the arrangement of things, we have magnesium, we have strontium, and then we have sulfur. Okay, the least conductive would be the thing that's over here on this side of the periodic table, which would be sulfur. So that would be my least conductive. My next conductive would be the thing that's the most furthest over this way, but as far as, maybe in the middle of the two. And we have magnesium and strontium right here. So my next most conductive would be my strontium. And then my most conductive would be my magnesium. So that would be the furthest one over here and up, giving me lots of metallic character. I think I read this wrong. I think this says silicon, doesn't it? It's not strontium. This is Si right here, which makes the answer so much easier to do. My apologies for not reading that correctly. Si right here is right on the staircase, so silicon right here would be the next, would be the middle conductor. They actually call those semiconductors, just like they're called semi-metals. So my magnesium would be my best conductor, my silicon would be my middle conductor, and my strontium would be my least conductive. Sorry about that, I just read the little letters wrong in there. On to number 30. Use the following to assist in the next three questions. So we have a balanced made-up equation of 3a plus 2b plus c goes to 2d plus e. And it says in question number 1, if there's 1 mole of each reactant, which is the limiting reagent? So to determine the limiter, remember, divide by the coefficient. And which one would end up being the smallest? 1 over 1 is 1, 1 over 2 is 1/2, and 1/3, of course, is the smallest. So letter A would be my limiting reagent when I divide each by its coefficient. Then in number 31, if 2 moles of B react with an excess of A and C, how many moles of D and E could be produced? So this is my 2 moles of B, and I'll do 2 equations, 1 for D, and 1 as my desired product being E. Put B in a position where it's going to cancel for both of them. And technically what I'm doing is the third step of a stoichiometry problem right here, because I'm given moles of B, 2 moles, and I'm desiring to know D and E right here. There's a 2 for a D, a 1 for a E, 2 for a B right here, 2 for a B right here, because there's always a 2. And so for D, 2 times 2 is 4, divided by 2, I would produce 2 Ds. And for E, 2 times 1 is 2, divided by 2 is 1, so I would produce 1 E. And so for 31, my best answer is A, 2 moles of D, 1 mole of E. Okay, number 32, 3 moles of A, so now I'm given 3 moles of A, reacts with an excess of B and C. If the reaction produces a 50% yield of reactant E, what is the actual yield of E? Okay, so first of all, I'll take my 3A and I'll compare it to E because I want to desire to know how much E is theoretically produced. So I put A in a position where it's going to cancel, and once again I'm doing like a mole-to-mole ratio right here. For every 1 E there are 3 A's. So 3 times 1 divided by 3 is 1 mole of E is theoretically produced. Okay? Now it tells me in the problem that it produces a 50% yield. So it really only produces half of what I mathematically predict it should form. So what's half of 1? Well, 0.5. And so that's letter D right here. It will really only produce a 50% 0.5 mole yield. And the last one on this page, number 33, says look at the reaction below, which lists the element oxidized followed by the element reduced. So this one, I'm just going to zoom in a little bit closer, and I'm going to go through it and assign oxidation numbers for each one of these reactants and products. So oxygen is -2, chromium then is going to have to add up to -2 with these. So this is a tricky math problem right here for some people. Oxygen's -2. There are 7 of them. It's going to have to add up to -2 up in the upper right-hand corner right here. There are 2 chromiums in this formula, and chromium has to be some charge. So something times 2 plus -14 equals -2. Oh, that means chromium here must be 6, because 6 times 2 would be 12, plus -14 is -2. Okay? Tin right here is +2. Remember, ignore the numbers that are in front and just look at the upper right-hand corner. If it has a number, that its charge. That's its charge. And hydrogen is +1. Over here on the right-hand side, chromium is +3. Tin here is +4. And oxygen is always -2, and hydrogen is +1 when it's with a nonmetal. And so I can see that chromium went from 6 down to 3. And so chromium was reduced. So my element reduced is chromium. Okay, I can see chromium's listed second right here. It's also listed second right here, so we're not quite sure of the answer yet. And then I can see that tin went from +2 to +4. So it went up in charge, and things that go up in charge are oxidized. And so my oxidized species is tin. And so that's why E is the answer, because tin is oxidized, chromium is reduced. Okay, my next page has my last problems on for this particular multiple choice practice test, and this has number 49, and it says, what is the maximum amount of copper that could be obtained from a mixture of 5 moles of CuO and 6 moles of carbon according to the balanced equation below? So we're given a balanced equation, and we're given a number of moles, and so now we're going to have to divide by the coefficient to determine the limiter, and then we can use the mole-to-mole ratio right here to calculate the amount of copper that could be obtained. Okay? Because notice all the answers are in moles right here, so we wouldn't have to do step number 4 in this. Okay, so I have 5 moles of CuO and 6 moles of C. And so in this balanced equation right here, Cu2O has a 1 in front of it, Cu has a 1 in front of it, and so whichever one ends up being smaller is my limiter. So this one limits Cu2O. Okay? So I take my 5 moles of Cu2O, compare that between Cu2O and the copper that I'm interested in knowing. And for every 2 coppers, there's 1 Cu2O. 5 times 2 is 10. So my maximum yield would be 10 moles of Cu, which is letter D. So look back again, because it's worded kind of weird in this one, and just see that it's a normal stoichiometry limiting reactant problem. They gave you the balanced equation. They gave you the number of moles of each reactant. You needed to divide by the coefficient to determine the limiter. It was easy because the coefficients were 1. And then I just did the mole-to-mole ratio between the limiting reagent and the substance that you desired to know, which was copper. Okay, that was number 49, and now we're on to number 50. Which is closest to the volume of a 0.2 molar sodium hydroxide solution that could be made from 20 grams of solid sodium hydroxide in an unlimited supply of water. All right, so molarity is equal to moles divided by liters, and the thing they want to know is liters because they want to know a volume right here. And if you look, all of your answers are in liters. If you forgot, a cubic decimeter is the same as a liter. Cubic decimeters and liters mean the same thing. Okay? Which is closest to the volume, so we're going to be looking for this. They give us this molarity right here, and they tell us that there's 20 grams of sodium hydroxide. Now that's not moles, but I could convert from grams to moles. So I could take my 20 grams of sodium hydroxide, put a multiply sign in a line, put grams in a position where it's going to cancel, and in 1 mole of sodium hydroxide there are 40 grams. Sodium is 23, oxygen is 16, and hydrogen is 1. And 23 plus 1 is 24, plus 16 is 40. So there's 40 grams in 1 mole. 20 times 1 divided by 40 means 0.5 moles of sodium hydroxide. Now, if I know I have 0.5 moles of sodium hydroxide, and my molarity is 0.2 molar, I could divide those two, and I could get the number of liters right here. So 0.5 divided by 0.2, let's do it on the calculator to make sure we don't make any mistakes. 0.5 divided by 0.2 is 2.5. So that means I could have 2.5 liters as my maximum amount, or what is closest to the volume. And that's letter D right here. Don't let the cubic decimeters confuse you. Cubic decimeters and liters are the same thing. And then the last one, number 51. A sample of a pure compound was found to contain this many grams of hydrogen, this many grams of carbon, and this many grams of chlorine. What is the empirical formula? So the empirical formula type problem is to take your number of grams, 0.25 grams of hydrogen. Now it's just the atoms of hydrogen because it's in a compound, so it's not going to be diatomic. 1.5 grams of carbon, it's just going to be the atoms of carbon once again. And then 8.875 grams of chlorine. Once again, just going to be chlorine. Once you have those number of grams, usually you have to assume a 100-gram sample, but in this case they give you a number of grams. You have to convert them to moles. So put your grams in a position where it's going to cancel. Put moles as your new set of units. Moles of hydrogen, moles of carbon, moles of chlorine. For every 1 gram, there's 1 mole in hydrogen. Look on the periodic table. For carbon, there's 12 grams in 1 mole. And for chlorine, it's 35.5. And let's go through and do the math on the calculator. This one I think you can do in your head. We'll have 0.25 moles of hydrogen. And in this one, 1.5 divided by 12 is 0.125 moles of carbon. And then 8.875 divided by 35.5 ends up being 0.25 moles of chlorine. Now, once I've got the number of moles of each one of the things that's making up the substance, I can divide by the smallest to determine the simplest whole number ratio with each one. And my smallest number of these 4 is 0.125. So I'll divide each by 0.125. This one ends up being 1, this one ends up being 2, and this one ends up being 2. Let's just confirm that 0.25 divided by 0.125 is equal to 2. Yes. And so my formula would be H2C1Cl2. Now it doesn't matter what order they go in, and so you can find out that the C actually goes first in all of the answers, and then the H is second, and then the Cl is third. And so letter B would be your empirical formula. All right, there is one of the multiple choices.